Hi everyone and welcome to our new video training package of Abaqus. Abaqus for Beginners, a comprehensive and example-oriented package for all beginners to Abaqus and finite element users. If you want to start analyzing your projects in Abaqus, it is better to save your time by watching this demo and making your decision easier. Don't waste your time watching amateur and weak videos on YouTube. This package contains 10 lessons in more than 400 minutes. Okay, let's go on to the next lesson content. Here I will present you the syllabus of each lesson and we can see some selected parts of them. In the first lesson, you will learn what is CAE software like Abaqus fundamentally and its related steps, pre-processing, processing, and post-processing. In addition, using units in Abaqus simulations is presented in Lesson 1. Take a quick look at the content of the first lesson. We must first answer this question: what is CAE? With the advent of technology, the use of computers in solving problems and making various products has been expanded. Computer-aided design, analysis, and fabrications are divided into three parts: CAD, CAM, and CAE. CAE consists of three sections: pre-processing, processing, and post-processing. We will explain each of these three sections in following slides. We want to introduce the software environment window in full details. We see the menu bar, toolbar, and context bar at the top of the software screen. The toolbox area has different tools depending on each module. For example, you can see tools related to part modulus in the figure. Well, for example, here you see a hinge with a pin on it. You can see in the figure all necessary actions that must be done in each module. For example, in the part module, our model must be designed or imported. In the property module, material must be created and assigned to sections. In the assembly environment, specify the position of the pin and the hinge relative to each other. An important issue in Abaqus software is applying units in Abaqus. Units are not specified in Abaqus and you must comply with the compatibility of the units. By specifying the unit of three quantities like mass, length, and time, the unit of the other quantities is determined based on their physical relation. You will know more about finite elements in Chapter 2 of this package. It is discussed how a finite element analysis will be done and how the software uses this theory. Degrees of freedom and some common elements in the finite element, such as plane stress and plane strain, are presented too. The validation discussion is done by convergence study and it is discussed in Chapter 2. Now let's look at the second lesson video. Let's take an example related to the simulation subject. Assume that the left side of the structure is fixed by these two holes and a force is applied to the bottom of right hole. And we want to calculate the amount of torque or stress in section AA. To do this, we can simplify this problem to a cantilever beam. How finite element works. First of all, our structure is divided into overlapping pieces, each of which is called an element. And each vertex of these elements is called a node. The second stage is that the behavior of each element will be formed. Its behavior is determined according to what type of element it is. There are different types of elements. Number 1, one-dimensional. Number 2, two-dimensional, such as triangular and rectangular element. Number 3, three-dimensional, such as pyramidal element and rectangular cube. All elements are connected by nodes, so some nodes are common. Errors that can be done by the user include selecting element incorrectly. For example, use shell element where solid element is needed. Another thing is that the points related to the generating of the element are not observed. In the third chapter, you will get familiar with the types of elements available in Abaqus. The beam element is used in this lesson and its types are introduced. We introduce characters and the degree of freedom of each element type in this chapter. Let's look at the third lesson video. The properties of the elements include the following: family, degrees of freedom, number of nodes, formulation, integration. Element family is actually the type of the element. Continuum element or three-dimensional element is for when we want to model a problem with real dimensions and size. Shell elements. In this element, the size of one dimension is much smaller than the other dimensions. We want to compare the displacement changes for a node at the end of the beam for all three analyses. To do this, select Tools, XY Data, Create from the main menu bar, then choose ODB Field Output. Select Unique Nodal as position and then choose U2, which is displacement in the Y direction. I hope you have enjoyed these lessons' contents until now. There are more amazing lessons. Be ready to check the next contents. In Chapter 4, you will learn about the different types of analysis at Abaqus. Analysis types depends on the type of solvers. For example, we introduce explicit and implicit solvers and explain their differences in problem solving using models and examples. Let's look at the fourth lesson video. The main differences between the two solvers can be divided into several categories. First, the element library, which Abaqus standards support more element libraries than Abaqus Explicit. In fact, Explicit solver has a subset of element libraries of the standard solver. As you can see, the explosion was not very strong. Therefore, the changes are not considerable. In fact, the explosion raised stress to 141 Pascal. I hope this tutorial was helpful for you. Good luck! In Chapter 5, we will explain explicit analysis in Abaqus. We will explain the methods of increasing the solution speed, including load rate scaling and mass scaling. Let's look at the fifth lesson video. Following tips are to increase the speed of solving quasi-static problems using the explicit solver. The first point is load rate scaling, which means loading in less time. The second point is mass scaling, or increasing the mass of the model virtually. To get an estimate of the best loading rate, we must first perform a natural frequency analysis on the model to obtain the natural frequency. As before, we compare internal energy and kinetic energy, which, as you can see, the plots show acceptable results. We also compare internal energy and total energy, which shows that the value of total energy is constant compared to internal energy. As a result, with this method, in addition to preventing the problem from becoming dynamic, we were also able to reduce the solution time. In Chapter 6, we will discuss linear analysis in Abaqus software. We will thoroughly explain the features of these problems, how to use them, and the two most common types, buckle and frequency analysis, along with their formulation. Okay, if you're ready, let's look at a small part of 6th lesson video. Abaqus uses 3 methods to solve the eigenvalues problem and to obtain natural frequencies. These 3 methods are Lanczos, subspace, and automatic multilevel substructuring, which is abbreviated to AMS. The Lanczos method is a traditional method used for traditional structures, which is the software default. It has more general capabilities than other methods, but is slower than the AMS method. To observe the behavior of the structure, the load proportionally factor diagram with relative to arc length shows the post-buckling location where the slope begins to change. You will learn cohesive behavior in Chapter 7 of this package. A cohesive element is usually used when 2 parts should be glued. Cohesive elastic and damage behavior, surface-based and element-based cohesive behavior are discussed here. Now it's time to check a short period of 7th lesson video. Once we reach the point of damage initiation, we will have reduced properties or progressive damage. If we want to calculate stress at any point in the reduced stiffness phase, we must use these relationships. The question is how Abaqus software uses these 2 methods. In the cohesive elements method, you have the nominal strain for separation, which is obtained by dividing the relative displacement between the top and bottom of the cohesive layer to the initial thickness. In this workshop, we are going to simulate a single lap joint under tension that is bonded using adhesive. The parts are made of steel and their dimensions are in accordance with the information here. As you can see in the result module, stress is 0 at the beginning of the analysis and increases over time. The cohesive damage index can be viewed by selecting the quad CRT option, which is based on the quadratic stress criterion. If you are a civil student, it would be interesting for you to know how to model damage for metals, composites, and concrete materials. In Lesson 8, you will learn many points about damage simulation in these engineering materials. In this lesson, we will focus on damage mechanics in civil engineering problems and some introductions will be presented. The choice of the suitable damage model depends on the type of material and the loading condition. If the model is brittle, you should look for damage models for brittle solids, and if your material has a significant plastic strain, using ductile damage models is the best choice. The model assumes that the equivalent plastic strain at the onset of damage, epsilon PLD, is a function of a stress reactionality and a strain rate. There are 4 damage indexes to determine which failure mode occurred. Damage will initiate when they exceed one value. When sigma 11 is more or equal to 0, fiber tension, and when sigma 11 is less than 0, fiber compression will occur. In case of sigma 22 more or equal to 0, matrix tension, and for sigma 22 less than 0, matrix compression will happen. In this regard, a reinforced concrete beam with FRP has been examined whose specifications are visible. Now we use Python code to create material concrete properties. The code is available in the package files. Nowadays, using composite materials is increasing in structural engineering. In the 9th lesson, the simulation of composite material is presented thoroughly. Main failure theories in composite materials, like progressive damage, are presented. A composite laminate can fail in two basic failure modes. The first mode is that the failure occurs in laminate due to interaction between layers, which is actually called delamination, as you know. In the second mode, the force of tension or pressure or shear causes the failure in a ply of composite individually. Stress experienced by the composite initiates cracks and causes delamination between the laminates and leads to more severe damage. E. Ozzie-Tsai-Hill theory. The Ozzie-Tsai-Hill failure theory is the same as the Tsai-Hill theory, except that the absolute value of the cross-product term is taken. This criterion is defined in 4 modes for tension and compression in the matrix and fiber. The equations of the 4 modes are these, as you can see. 4 different modes of failure are considered: fiber rupture in tension, fiber buckling and kinking in compression, matrix cracking under transverse tension and shearing, and matrix crushing under transverse compression and shearing. If we want to see, for example, the stress changes in all layers in the thickness of the sheet at this point, it can be seen for the option X data and thickens. One of the most important issues in simulating damage behavior is the hardening issue. In Lesson 10, some main points about the different types of hardening and hysteresis loops and graphs are presented. Now let's look at the final lesson video. What is hardening? First of all, we should explain what is the yield surface. In the general 3D, all 6 components of a stress tensor contributes to yielding of the material. The von Mises equation in yield condition has this form. If we subject all stresses in the third direction to 0, the plane stress yield condition becomes this. In the principal coordinate system, sigma 1, 2 is equal to 0, and the yield condition takes a simple form of this equation, and the related graph is shown here. The yield surface defines the elastic region of a material under different states of stress. When the stress point is situated within this surface, only elastic strains are produced. When the stress point is situated on the yield surface, this equation is satisfied and plastic strains are produced. Hardening is known as work hardening and strain hardening because plastic deformation results from the movement of these locations in material microstructure. Metals can be strengthened by preventing this motion. In this workshop, several parts must be designed. So in the table, we will have 2 separate H-beams with the following geometric dimensions. Here, result of our simulation. In order to plot the hysteresis graph, go to Create XY Data, then continue with ODB History Output. After that, use Combine function and the U1 and RF1 for its indices. then plot it. I hope you have got enough information about this package, but don't worry at all. If you have any questions about this tutorial, ask us via support@caeassistant.com. Our support is one of the main advantages of Abaqus for Beginners package compared to other Abaqus tutorials on the web. You can watch all lessons, and when you are simulating your project, ask your question from our support and get their help. Take it easy to solve your projects in Abaqus and enjoy it!